All right, and now the real fun begins with some more derivative rules involving when we have functions that are being multiplied or divided. And the big question that we're going to tackle in this video is, do you do the algebra now or do you do the algebra later? And that's a decision that you will have to make based on some comfort and based on also just what makes sense to get the problem done efficiently. So as we talk about this, we're going to discover there's more than one way to do the problem, but we also know that some ways are more efficient than others. So we've got two different functions that are being multiplied together. We can take the derivative by taking the derivative of the first times the second function, and then we take the first function and then multiply it by the derivative of the second function. And that's how you do the product rule. You're basically taking as many different terms of products of functions, and then you take the derivative of each function one at a time in these terms. And when you see it on the next slide, you'll understand a little bit more what I mean. Version of the product rule, but some people, and by some people I really mean me, prefer is u prime times v plus u times v prime. And that it kind of rolls off the tongue a little bit easier and easier to remember. All right, when you're multiplying three or more functions together, this is when the product rule gets a little hairy, because you're dealing with three functions, f, g, and h, multiplying them together. Well, you need to differentiate f first and then multiply it by g and h, and then add in f times the derivative of g times h, and then f and g times the derivative of h. And you can see that if you've got a function there, you're multiplying several different functions together, or God forbid you've got a situation where you're raising something to a big power, you can tell that this is going to get pretty hairy in a hurry. So in order to handle this, we're going to try to keep these simple applications of the product rule, and we might develop some other strategies for other types of functions a little bit later on. Okay, so here's what we're going to do. We're going to do the example here of differentiating the product of these two functions, and I think this one example is all you really need to see here. So we're going to call this function f of x squared plus 1 times the quantity x third plus 3. We're going to call this the u in our formula, and then we're going to call this the v. So if our formula for the derivative, if it's going to be u prime times v plus u times v prime, you're just going to have to fill in those spots with what those things are. So I'm going to start with u prime, and the derivative of u looks to be just 2x. And then what I'm going to do is multiply it by v, but I'm not going to differentiate v, so x third plus 3. Now what I do for the second part is I just reverse that process. I'm going to start with my u function, which is x squared plus 1, and now I'm going to differentiate my v, which looks to be 3x squared. Okay, so now that we've got these all taken care of, why don't we go ahead and apply the distributive property and then see if we can get a bit of a cleanup here. So it looks like we're going to have 2x to the fourth plus 6x for the first distribution. And then over here it looks like it's going to be 3x to the fourth plus 3x squared. Okay, so now that we have those things out of the way, I can go ahead and clean up the like terms, and then my derivative looks to be 5x to the fourth plus 3x squared plus 6x, and there it is. Not difficult to do, maybe just an interesting step or two of algebra, but nothing you can't handle without a problem. Okay, now here's the other question here about this, and it is, could you possibly find the derivative without using the product rule? Yeah, I probably could end up in the same spot here as f prime, and the way I would do that would be to FOIL those two together. Okay, so very quickly, if you were to FOIL f of x out, you would end up with x to the fifth, and then you would get an x to the third, a 3x squared, and then a 3. And I think you would quickly see that the derivative would be 5x to the fourth plus 3x squared plus 6x, and then the 3 drops out, and oh, surprise, look, it looks exactly like what happened when we got the product rule. So really, I didn't necessarily have to do one way or the other. It just depends on what your comfort level is, and honestly, if there's more than 3 terms in one of these polynomials, I'm probably going to reach for the product rule. All right, so now we've got the quotient rule where 2 functions are being divided, and if one of them isn't 0, then we can figure this out pretty easily. Okay, so to do the quotient rule is kind of interesting because you could almost derive it by doing the product rule and rewriting what the denominator is 1 over v. But I'm going to go ahead and speed up the derivation and tell you that this is going to be the derivative with respect to x of u times v minus u, let me put that in brackets there, times the derivative with respect to x of v, and then this is all going to be over v squared. Okay, so if you stop and think about your power rule for just a second, it makes a lot of sense that when you are taking the derivative of something that's got a power of 1 downstairs and ends up with a power of 2 downstairs, lower the power by 1. So this is kind of a fascinating little rule here. It kind of looks like the product rule at first up top, but you're subtracting, and then you're dividing everything by your v squared, your denominator squared. Okay, so a little trick to remember the quotient rule, with all apologies to Cab Calloway here, is going to be low d high minus high d low all over low squared. Okay, now the high and the low refer to the numerator and denominator respectively, and anytime we see a d, that's going to be to indicate to take the derivative. Okay, so let's kind of sing along with Cab Calloway as we do this quotient rule problem example here, and we differentiate x to the third minus 1 all over x squared plus 1. Okay, so let's wander through the formula here and see what comes out of this, because you just never know. So your derivative is going to be low function, x squared plus 1, times the derivative of the high function, 3x squared, minus the high function, x squared minus 1. Let's clean that up just a touch. And then the derivative of the low function, which should be 2x. And then this is all going to be over taking what's in the denominator and raising it to the second power. Okay, so now this is a case of algebra later. We've done the calculus steps, so now let's clean up the algebra and see what we get. So we're going to get 3x to the fourth plus 3x squared when we distribute. And then it's going to be minus 2x to the fourth. And then if I get this right, it should be plus 2x. And then this is all over x squared plus 1 quantity squared. All right, moving ahead to make sure we get everything the way we need it to. It looks to be 2x to the fourth plus 3x squared plus 2x, and this is all over x plus 1 quantity squared, and that's all the further I want to take it. I certainly don't want to try to reduce this down. I can't do that unless I can get a factor of x plus 1 to turn up, And I don't think it will, and B, I'm just a little too lazy to do the factoring and see if it happens anyway right now. I mean, if it does, great, but I'm not optimistic. Okay. So liberal use of parentheses is definitely recommended for all the types of differentiation problems. You've seen me use it a couple of times already where I throw in extra parentheses. And with the quotient rule, it's always a good idea to enclose all of your numerators and your denominators in parentheses. And pay special attention to the subtraction that you need to do in the numerator. You got to distribute that negative, otherwise you're going to be in a little bit of trouble. Let's do one more example. X to the third minus 3 over x plus 1. Okay, now there is another way that we could definitely attack this problem. Okay, we could certainly attack this problem by using polynomial long division, but I don't think anybody really wants to do that. So I'm just going to go ahead and do the whole Cab-Calloway thing. So this is low d high minus the high function times d low, and this is all over low function squared. Okay. Well, let's distribute out here. We've got 2x squared plus 2x minus x squared plus 3, and then this is all over x plus 1 quantity squared. So now we clean up a mess even further, and we get x squared plus 2x plus 3 all over x plus 1 quantity squared. Okay, I'm afraid this isn't going to factor. We're really tempted to think that x squared plus 2x plus 3 will factor. It will not. So I'm just going to stop right here and call it good. I would also say that there's really no need to FOIL this unless you think it's absolutely necessary. You might as well just leave it alone. Okay, now, students in mathematics, once they get taught a new trick like the quotient rule, they tend to think that every single problem that looks like what we just did is a candidate for being using the quotient rule. Okay? And I say to you, be careful, because you might buy yourself a method that, while it could lead you to the right answer, you may not always end up there if you make mistakes, or if you realize, oh, this isn't quite the same application as what I saw, so now I'm a little uncomfortable, and yeah. So here's a good rule of thumb. When there is only one term in the denominator, that is probably the best signal that you can use the quotient rule, or avoid using the quotient rule, rather, okay? So it can be easily rewritten as something that no longer necessitates a fraction, and then you simplify first, and then you don't use the quotient rule. This may lead to heartbreak and misery if you choose the wrong thing. Okay, so let's run through and make sure we're clear on this. This first one in A has exactly one term. Okay, it has exactly one term. So I am not going to use the quotient rule. Okay, so what I'm going to do is I'm going to break this up into two parts. I'm going to break it up into 1/6 x squared plus 1/2 x. Now, where am I getting the 1/2 x? Because 3 over 6 reduces to 1/2. Okay, so now that I've done that, I can avoid the quotient rule altogether, and I can turn my focus on the derivative dy over dx. And that is going to wind up being, okay, well, 2 over 6, that's going to be 1/3 times x plus 1/2. And that is where I should probably stop. And that was a lot easier than using the quotient rule because, again, we only had one term. Okay, now in part B, you will want to use the quotient rule. There's more than one term. So let's run through the process and see what happens on a part B here. So our derivative dy over dx is going to be the low function, x squared minus 3x, times the derivative of the high function, That's just going to be 1 because the high function is just an x. Okay, then it's minus the high function times the derivative of the low, so 2x minus 3. And then this is all going to be over x squared minus 3x, and I'm going to raise that to the second power. All right, so let's do a little bit of cleanup here, and let's see what happens next. We're going to have x squared minus 3x minus 2x squared plus 3 all over x squared minus 3x quantity squared. And then last little bit of cleanup later, negative x squared minus 3x plus 3, and then x squared minus 3x quantity squared at the bottom, and that's all there is to that. Okay? All right, now for this last one here on h of x, you'll notice there's only one term. So let's just go ahead and break it up into 3 different parts and get it done. So if I break this up, it's going to end up being, well, let's see, x to the third over x squared. That's just going to be an x. And then an x squared over an x squared. Those are going to cancel, so minus 3. Kind of happy with this so far. But then I'm going to rewrite this because it's going to be 4 times x to the negative second. Okay, and the reason why I want to do that is because I want to make applying my power rule a little bit easier in the end. So now I can go ahead and take the derivative, and once I do, I'm going to get 1 minus 8 over x to the third power, and there is that. Okay, so the big lesson here is if there's more than one term downstairs, use the quotient rule. If there is only one term downstairs, try to break it up into different fractions and make it easier on yourself that way. Sorry about the line break on this, but here we go. A couple of thoughts here to keep in mind. You will notice that algebra will have to be done regardless of when you do it. So the best thing for you to do to make a strategic decision is when to do the algebra. So sometimes this means you'll need to look 2 to 3 steps ahead to decide what works for you. All right, now here's the line break problem. The biggest mistakes that students make on these problems is in simplifying. Just because you're doing calculus doesn't mean that all the rules of algebra get thrown out the window. Every rule that you learned about algebra up until now still applies. Okay. So, quotient rule or not to quotient rule, that is the question. And now we want you to avoid the slings and arrows of outrageous math. Sorry for another Hamlet reference, but sometimes we have to do it. And here's the task, finding the equation of the line tangent to the curve. Y is equal to x squared plus 3, and that's going to be divided by 2x. And when I see this, the first thing that comes to mind is I probably want to do the breaking up trick, because I got the point, I just need the slope. So let's just go ahead and break this up. And then when I take the derivative, dy over dx, I'm going to get 1/2 minus 3/2 x to the negative 2. And simplifying that is going to lead to 1/2 minus 3 over 2x squared. And now I need to know what the slope is when I have 1. Well, if I have a 1 as my x coordinate here, and I put it in, it's going to be like 1/2 minus 3/2. So that's going to be negative 1. So dy over dx, when x is equal to 1, that's the same thing as saying negative 1. So now I've got my slope, and I've got my point, and we can put all this together. So it's going to be y minus 2, and then negative 1 times the quantity x minus 1. And this, friends, This is our tangent line. Not bad at all. A couple more things here on this. First of which is working with numerical values on AP questions. So I've got some functions here that you don't know what they are. All you know is that you've got a u of 2 is equal to 3, u prime of 2 is negative 4, v of 2 is 1, and v prime of 2 is 2. All right, so I think I could probably solve these questions out, because if I'm finding the derivatives at 2 for all of these functions, well, the derivative in A by our constant multiple rule is just going to be 2 times u prime minus 3 times v prime. It's just going to be those derivatives there. And at an x value of 2, I know what those derivatives are worth because I've got them right here and right here. So now I'm going to sub those in, and we're going to see what happens. Wow, a rather large negative 14. Okay. So probably for u times v, we'll use the product rule. So our y prime is going to be u prime v plus uv prime. All right, u prime, according to the problem, is negative 4. And v is going to be 1. And then u is going to be 3. And v prime should be 2. Okay. So getting a little simplifying here, negative 4 and then plus 6 should end up with 2 at the end, I believe. All right, now we've got this one here with the quotient rule. So if I want the derivative of that, that's going to be low times the derivative of the high minus the high function times the derivative of the low all over low squared. Okay. Or in this case, v squared, I guess. So let me back up and write that in as a v there. All right, so let's go ahead and plug in the values here. V is 1. U prime is negative 4, as we already know. And then u is going to be 3. And v prime is going to be 2. And this is all over v squared, actually. So if v of 2 is 1, then 1 squared is just 1. And now I could do a quick cleanup here. So negative 4 minus 6 all over 1. I think we should end up getting negative 10, if I am not mistaken. So that's your u prime v minus uv prime all over v squared. That's going to be your quotient rule right there. Okay, now why did I go over these? Because this. Beware. It's probably going to be on the test. Don't say I didn't warn you. All right, now a really easy concept to wrap up this lesson, and it has to do with second and higher order derivatives. The second derivative is very simply the derivative of the derivative. So you can just keep going on derivatives as long as they have positive integer order. So the third derivative is always the derivative of the second derivative of the first. First derivative is just the derivative of our original function. So let's see if I can find the third derivative of x to the third power. Well, to get the third, you need the second, and to get the second, you need the first. So the first one is 3x squared. The second one, consequently, will be 6x, and therefore the third one, that works out to be just a constant 6. Okay, pretty easy to do. All right, so what I want you to do is pause the video here and try this and see if you can come up with the first four derivatives of x to the third minus 5x squared plus 2. Go on, pause the video. I'll wait. You haven't paused it yet. There's no need to lie to me. I work here. Okay, pause it now. Okay, and here they are. The first derivative is 3x squared minus 10x. The second derivative, and that's denoted by powers of 2 in your Leibniz notation. You could do 2 tick marks if it were an f double prime of x, for example. That's 6x minus 10. The third derivative would then be 6, and the fourth derivative would then be 0. Pretty easy to do. Okay, so give some practice problems a shot, and we will see you in class.